is MSE 5033 Composite Materials lecture number 3. This is divided into two sections. The first one talks about the fracture mechanics and the importance of adding composite fibers or second phase particles into a matrix material in order to toughen the material or to make it be able to deflect the cracks. So that's where we will start with. So the first part of this lecture will deal with that, and the second one, and going forward, we will talk more about processing of composite materials itself. So some basic ideas of fracture mechanics. Some of you, it already may be known to you. So when does fracture happen? Fracture happens when the applied stress exceeds the fracture stress, and the fracture stress actually goes down if there are cracks present in the material. So cracks and their sizes play a very important role in determining the properties of any material, especially brittle materials. So for the same part, the fracture stress may be different depending upon the crack size, and this is the basic phenomenon or information given by what is euphemistically called the Griffith criterion. So in any material, we know that cracks are caused by microstructural flaws. In the simplest form, if you have an inner crack, you have a crack of critical length 2A if it is an inside crack. Okay, and it has to, as it is being pulled in the normal direction, those crack edges are opened up and it creates new surfaces being formed. So as the crack is being opened up, it will fail if it reaches the failure stress, and so it can be technically represented as sigma greater or equal to sigma f, which is equal to a function of the crack size A. And so in the inner crack, you have the critical flaw size, the flaw size as 2A, but still you can represent the failure stress as a function of A. So when it is being pulled, the bonds are ruptured and the crack size is beyond a certain size, the crack extends to the sides and it makes the material fail. So you need energy to create new surfaces or to open up the crack itself. And there is also other energy that goes into a zone around the crack, and that zone is called the process zone. And that zone, the size of that zone will depend upon the type of material you have. So there are two ways to approach that. So you can either say that there is an inside crack or there is a surface crack, and both of them are connected. So the first one, there are two ways to do that. The first one is by the thing we call stress intensity factor, or the second one is based on energy balance, which is more thermodynamics based. The most important or the most conservative form of loading is tensile loading or mode 1 loading. And so the easiest way would be to use mode 1 loading for the analysis. And just to keep it simple, um, we will limit ourselves to plates, and we will say that it is loaded along the crack axis and the cracks are in the center or in the edge. There are other ways to load the components, but like if you have shear stresses in mode 2 or mode 3, but you still use the mode 1 because that gives you the lowest value of stresses required to make the material fail. So if you have a flaw at the edge of the crack, there is a stress concentration. We know that there is a stress concentration at the edge of the crack, and you can assume that very close to the crack tip it has a finite radius of curvature, and when that crack is sharp or very sharp, then that radius of curvature is equal to 0 or close to 0. And most of the time, I'm not going to go into great detail or depth about this, but there are well-developed techniques to analyze such cracks under LEFM techniques. But the thing to note is that these solutions are very easy to derive for 2-dimension, but extremely difficult to set up and solve for 3-dimension. So the general form of the solution is equal to the stress at any given point Ij is equal to a constant K or 2 pi R, where R is the distance of the point where we are measuring it to the crack tip, and the angle at which is theta. So you can say that it is Fij, it's a function of theta, plus there is a non-singular part also. So this is the general form of the solution derived by linear elastic fracture mechanics. So what is to note is that, so you have a singular part and you have a non-singular part. So the most important part in LEFM is the singular part. It is proportional to 1 over under root R. And as R tends to 0, so as close to the crack tip as possible, then this tends to infinity. What really matters is the stress intensity factor for any given material, and that can be represented to be equal to a constant beta times sigma into under root pi a, and it depends upon the stress and stress state. So beta is a geometric constant which depends upon the loading conditions and the plate geometry. For inside cracks, beta equal to 1, and for edge cracks, beta has been derived to be equal to 1.12. So where is it more critical? It is more critical in the case of ceramics and glasses, which do not have any kind of plastic flow, or sigma y is approximately equal to infinity. So at the crack tip, if you increase the stress large enough, then those bonds can be fractured and the cracks can just advance and progress further. Our argument is that since K scales as sigma ij, whatever goes on at the crack tip must be resulting from sigma ij or fracture occurs at a critical value of K. So you have a critical stress intensity factor for every material. It is a material property. So that is the critical stress intensity factor which determines the stress at which the fracture will occur. So if K1C, or the critical stress intensity factor in mode 1, is equal to K, it is considered to be a material property. So in realistic terms, if it is an ideal brittle material, it will be related to the value of energy required for creating a new surface. So essentially what we are saying is that fracture will occur when the stress intensity factor is equal to the critical stress intensity factor for that material, which has been determined experimentally. And that has been derived to be equal to a value stress, failure stress times under root pi critical flaw size, which is equal to K1C. So which means that at the critical stress intensity factor, the flaw size will be equal to the critical flaw size and stress will be equal to the failure stress. It has been determined that for extremely brittle materials and glass, especially glasses, silicon crystals, etc., you have pretty low critical stress intensity factor of about half to 2 megapascals per root meter. Please note, megapascals per root meter is the unit for the stress intensity factor. And for engineering ceramics, you have numbers ranging from 1 to 4. What is to be noted here is that the failure stress and critical flaw size have an inverse dependence. That means if you have a small flaw size, then you will have the failure stress that is pretty low. So let me stop here for the first section and we will continue in the next section after this.